Hello, Professor Sargent here with you again. This is another Math 101 flipped classroom lesson, and we're talking about the first half of section 7.3. Because we have now seen a relationship between radicals and writing something with an exponent that is a rational number, a reduced rational number, by the way. When that nth root over here exists, then we can say these are equal. Well, there are some exponent rules that we just recently talked about, where if you have multiplication or division inside, you can, for lack of a better word, distribute the exponent. However, we cannot do that for addition or subtraction. It just works for multiplying and dividing. Because of this relationship between radicals and rational number exponents, then we can say that we have the same kind of rules, allowing us to either put together two roots with the same index that are being multiplied. We can put them together as a single nth root with multiplication underneath, or we could read it the other direction and break up what we have here. It may be that that allows us to simplify. That's called the product rule, and we also have a quotient rule. Again, we have to be talking about the same index n here, here, and here. You can either put a quotient together under a single nth root or break it apart. So, using the product rule on this first example, square root of 7 times square root of 7. We can put 7 times 7 underneath a single square root, and that's 49. So we're supposed to take the square root of 49. That gives us 7, which may not be a surprise for some other reasons. Whereas this may not be so obvious what's going to happen. If we take the 18 and the 2 that are underneath the individual square roots, multiply them under a single square root. Well, now we're looking at the square root of 36, and that is 6. Even if we have a variable, we can still apply the product rule. Multiply the 10 and the y underneath the single square root. It doesn't have to be just square roots. Here we have 2 cube roots. So multiply the 3 times the 2 under the cube root. That's 6 underneath a single square root. Now that's not going to be able to go any further than that. I will explain shortly with some of these later examples. In number 5, we're using the quotient rule to break this up, which is nice because both 16 and 121 are perfect squares. We'll do a similar thing here in number 6, but the 5 is not a perfect square. 16 is, the square root of 16 is 4. To give a little bit of an explanation about why I didn't do anything more in number 4, 5 is not a perfect square, and its only perfect square factor is a 1. If I had a larger perfect square factor, I might have been able to do something. Here, the only perfect cube that goes into 6 is 1. All right, use the quotient rule to split this up. Not only is 25 a perfect square, but with that even exponent, x to the 12th is also a perfect square. Off on the side, I could think of x to the 12th underneath the square root being the same as x to the 12 over 2, which will reduce. So we have x to the 6th over 5. Then in number 8, break up that quotient. Cube root of r squared over cube root of 8. Part of why I won't be able to go any further here is because that exponent is less than the index of the root, whereas the cube root of 8, that's 2. So I leave the numerator as cube root of r squared and simplify the denominator because it's a perfect cube. Okay, let's see here. That negative, although we have a fourth root, an even index, that negative is outside. So we can simplify this. It's a -1 times the fourth root of 256 over the fourth root of x to the 8th. So let's see here. I know 16 squared is 256, and 4 squared is 16. Multiply those two exponents. 4 to the 4th should be 256. Give me a moment and I will check that. All right, here we go. Is 4 to the 4th 256? And yes, it is. We could have also done the following. Type the index first, and then second, and the exponent above that is the xth root, or nth root as we usually call it. So the fourth root of 256, we are getting 4. All right, so let's use that and continue simplifying. Fourth root of 256 is 4, and we had that negative tagging along out in front. Furthermore, just like on this one, we had x to the 12th under a square root. Remember, the index of a square root is 2. We divided the exponent by the index and simplified that to x to the 6th. So here, dividing the exponent by the index, 8 divided by 4, we'll get 2. It's telling me this is -4 all over x squared. Now, for the rest of these, things aren't going to simplify quite as nicely. It's going to be similar to what we had here. 32 is not a perfect square, but the largest perfect square that will go into it is 16. It goes in twice. If I were able to get a larger perfect square factor of 32, then I would have been able to break it off of this factor. And the only perfect square that goes into 2 is 1. We can talk in class about some other options about how to look at this, but it boils down to breaking that as 16 times 2, break up into individual square roots, take the square root of the part that you can, the perfect square, square root of 16 is 4, and then times square root of 2, which we can't do anything to simplify. Similar here. That negative, by the way, is not in the square root. It is out in front. So just like with this, we've got -1 times this, really. The largest perfect square that will go into 98 is 49, and it'll go in twice. So I split that up into -1 times square root of 49 times square root of 2. The square root of 49 is 7. And so -7 square root of 2. On the next one, cube root of 2,160. That extra 0, if I look at just the 216, I'm recognizing perfect cube. 6 cubed is 216. So I'll break up 2,160. That's 216 times 10, still all underneath a single cube root, and then split up into individual cube roots. Cube root of 216 is 6. Cube root of 10, there's no perfect cube that is a factor of 10 besides 1. That's not gonna help us break things down any. Looking at number 13, that ends in 5, so I know 5 will go into 135. In fact, it goes in 27 times. Not only that, 27 is a perfect cube. It's the largest perfect cube that will go into 135. If there was something even larger than that, I would have been able to get it out of the factor of 5. But the only perfect cube that goes into 5 is 1. So I split that up into cube root of 27 times cube root of 5. And that's cube root of 27 is 3. So we've got 3 times cube root of 5. By the way, some of you may have calculators that when you have numbers in there, will be able to answer most or all of these. However, you then will not be able to deal with when there are variables. So I insist on this kind of work being shown in order to get full credit. Finally, on this last one, that 0 at the end, maybe we could look at 32 times 10. You may not know any perfect fifths, but 1 to the 5th is 1. 2 to the 5th is 32, so that's going to take care of that factor. And it's also telling us that we've jumped past any perfect fifths that might be factors of 10 besides the 1. A factor of 1 doesn't help us change anything. So I use the product rule to split that up. -1 times the 5th root of 32 times the 5th root of 10. 5th root of 32 is 2. So I've got -2, 5th root of 10. There will be a second day of learning about this stuff. Going to push the things about the product rule and the quotient rule a little further. That's in a second day of class, a second assignment. And so this is all I've got for now. Hope it helps, and I'll see you in class.